In section 2.5, we explore a specific type of application problems that are called variation problems. So there are three main types of variation problems. And of course, you can combine any of these types together to create another variation problem. But the three main types are direct, inverse, which is also known as indirect, or joint variation. So when we talk about a direct variation, what you're talking about are two quantities that as one increases, the other quantity also increases. So what this is saying is that if x gets bigger, y also gets bigger. And so we can write that as y equals k times x. So if x gets bigger, y gets bigger. But what is k? Well, k is what we consider to be the constant of variation. It's the fudge factor we use to set two things equal to each other. It's also referred to sometimes as the proportionality constant. I'll call it the constant of variation. And we usually use a k. You can use any letter you want, but our textbook and most mathematicians use a k. So this is simply saying that as x gets bigger and bigger, y will also get bigger and bigger. And you can see that because y is just this constant, which is a constant like pi or 5 or negative 2.9 or whatever. But as x is getting bigger, k times x will make y get bigger also. And that's a direct variation. You also have something considered to be an inverse variation or an indirect variation. And what you'll notice this time is that x is in the denominator. So what happens here is that as x gets bigger, y is going to get smaller. And that should make sense because if you think about the denominator of a fraction getting larger and larger and larger, the overall fraction gets smaller and smaller and smaller. So if you think about 1/2 versus 1/3 versus 1/4 versus 1/5, so the larger the denominator, the smaller the fraction. That's what this is saying. Notice that constant variation is still sitting there. And then finally, we have a joint variation. So what happens with a joint variation is y is going to depend on more than one other variation or variable, in this case, an x and a z. So in this case, we have y is equal to k times x times z. In general, a joint variation is a product. Unless it specifically says some other word, you're going to multiply whatever is there. Okay, we can see again that if x and z are increasing, y is going to increase. I can also say that if x is decreasing, then y would decrease here, and the inverse would be half true here. If x decreases, y would get bigger. So as the fraction gets smaller and smaller and smaller in the denominator, the overall result is a larger and larger result. So the first thing we're going to do is try just writing the equations and solving for k. And that's usually the nice first step when you're doing variation kinds of work. So example 1 simply tells us, write a general formula to describe each variation. So it says v varies directly with t. So in part A, v varies directly with t. So I'm going to stop right there because I see the word direct. I know exactly what to do. I'm going to start off with the first letter they give me, which is v. The next will come the equal sign. Immediately after the equal sign, I throw in my constant of proportionality, or my fudge factor, as I like to call it too. So there's my k. And then because it says directly, whatever comes after the word directly is going to go right next to k, and that's a t. So that right there represents the very first part of the problem. V varies directly with t. Now they're going to give me a set of numbers in order to be able to calculate t. So the first step is to write the variation equation. And our second step is now we're going to use the first set of values to find k. And sure enough, in this problem, it tells us specifically v is 16. So we're going to replace v with 16 when t is 2. So I kept k there, and I'm going to replace the t with the 2. And now we just need to solve it for k. So k is 16 divided by 2. K is equal to 8. So I now know what the constant of proportionality is for this particular set of circumstances. So now I can rewrite the equation. So step 3 is to rewrite the equation with the number in place of k. Now when we start doing the actual applications, we'll add on a fourth step. But for right now, all we're doing is saying v is equal to 8t. So if you give me a value for t, I can give you the value for v. Or if you give me v, I can find t. And that's a direct variation. Our next example, part B, reads, Here it says f varies inversely with the square root of r. F varies inversely with the square root of r. So the first thing we see is f. That's the first thing I'm going to write. Immediately go for my equal sign, and then I'm going to have the k. Then it says the square inversely. Inversely means whatever follows that word is going to go in the denominator, the square root of r. So now we have the square root of r, and that's all that sentence tells me. Again, f varies inversely, meaning what comes after the k is in the denominator with the square root of r. And then they give me again a set of numbers. They tell me that f equals 4 when r equals 9. That would be 4 is equal to k over 3. We're going to clear the fraction, multiply everything by 3. And we get k is equal to 12. So f is equal to 12 over the square root of r. So again, you give me another r, I can find an f, or you give me an f, I can find the r. And there it is. These problems work really well in terms of physics and chemistry as you relate different things together, pressure and temperature, or speed and distance, those kinds of things. Part C on that problem tells us that t varies jointly with the cubed root of x and the square of d. So t varies jointly. So again, I'm going to start off with my t. Varies is the verb. That's my equal sign. I immediately put k in. Jointly tells me that whatever is following that needs to be multiplied together. It says the cube root of x. That would be the cube root of x. And now that's times the square of d. So d squared. There's no good way to write that so that it looks good. So I'm going to actually use a dot for multiplication in there. And there's our equation. So t is equal to k times the cube root of x times the square of d. They then tell me that t is equal to 18 when x is equal to 8. So I'd have the cube root of 8. And d is equal to 3. So that would be 3 squared. So let's clean up that right side first. Cube root of 8 is 2. 3 squared is 9. That's going to give me 18 is equal to k times 18. So in this case, k is equal to 1. Doesn't happen very often, just a set of numbers. So now we can rewrite our equation. T is equal to 1. I'm going to put it in there just so you can see what we did. Times the cube root of x times d squared. There's your equation. Okay, one more before we start the actual application. So part D is the square of t. So this time it's not just a t, it's a t squared. Varies is my verb. So there's the equal sign. Then we'll immediately put our k in. Directly with the cube of a. So that would be a cubed, and because it says directly, I know it goes next to the k. Inversely tells me that now we're going to go to the denominator, the square of d. So the square of t varies directly with the cube of a and inversely with the square of d. So again, you can combine them together. So that tells me that t is equal to 2. So that would be 2 squared is equal to k times a is also 2. So that would be 2 cubed all over 4 for d squared. So that would be 4 is equal to k times 8 over 16. Well, I'm going to do some canceling because that's just easiest on me. So I canceled the 8 and the 16 and got a 1 and a 2. So k, sorry, 4 is equal to k over 2. So k is equal to 8. Again, I multiply both sides by 2 for that fraction. So then our equation becomes t squared is equal to 8, replacing our k, 8 in the third over d squared. Now, these beginning problems are designed to work with a nice value for k, but in the real world, the values of k are not nice. Additionally, for our purposes in this section, we're going to assume that k is unitless. That's not true. K has units, and it's the correct units that make the left and the right side work out in terms of units. But since we don't do the dimensional analysis in this course, we're going to gloss over that and just consider k to be unitless.